Hello and welcome to the presentation of our Mechanical Engineering Senior Design Project. My name is Will Albright.
My name is Daniel Bulerin.
My name is Drew Campese.
My name is Julia Sheiber.
My name is Dillon Tomazin. We are here today to provide insight into our project scope, design choices, actuation methods, and present our final prototype model as well as what we've learned throughout the year. When Senior Design 1 began in January of 2024, we were tasked with creating a set of retractable bird claws that could attach to an unmanned aerial vehicle or glider. Birds have been on Earth for over 150 million years and have been the source of inspiration for the majority of advancements made within the aviation industry. Current aviation designs require open, flat areas for aircrafts and drones to properly land, which is not always ideal. By applying bird perching capabilities to a drone or aircraft, we propose the opportunity for many new applications. A drone with these perching abilities allow for advanced military surveillance, reconnaissance missions, and assistance during emergency situations.
Birds have developed various defenses and evolutionary advantages in order to effortlessly glide across the sky and perch wherever they please. As engineers, it is important to acknowledge the principles and mechanics of pre-existing natural designs in order to create optimized solutions. Biomimicry is a study that involves mimicking the strategies and patterns found in nature in order to solve human design challenges. Considering that this is a biomimicry design, our first step was to familiarize ourselves with the anatomy of various birds, landing gear, grasp strength, and flight dynamics involved during bird perching.
After conducting research about birds, we benchmarked designs for research papers that explored similar design scopes. Our two main sources for design inspiration came from Stanford University and Qingdao University of Technology. Both universities published papers with claw designs that studied variable perching and grasping capabilities. This provided us with initial direction and inspiration for our actuation methods and design techniques. The design we decided upon includes a driving structure that can attach to a fuselage of a UAV or a glider, two retractable legs, and two bird claws.
The two primary bird claw digit configurations we considered for our design were anisodactyl and zygodactyl. Anisodactyl is ideal for birds that perch, swim, and hunt, whereas zygodactyl is better for birds that climb. Considering that our goal was to achieve variable grasping capabilities, we incorporated the anisodactyl arrangement into our design. This toe pattern features one front-facing digit, one rear-facing digit, and two diagonal front-facing digits. Each digit is connected to the palm structure with a design intent to connect the proximal toe bones of each digit and the legs. The bottom surface of each toe bone is curved in line with the frictional rubber material, mimicking the padding that birds have on their claws. The padding ensures that the claw will make complete contact with the grasping surface and decrease chances of slipping while perched. The superior surface of each toe bone has a channel which allows for a cable to be guided through. This cable will be in direct connection with the linear actuator to create the necessary displacement that drives the claw open. The joints of the claw are the junctions between each of the toe bones, and they allow for curling motion. Each joint corresponds with 1 degree of freedom. The front-facing digit has 3 joints, the rear-facing digit has 2 joints, and the diagonal-facing digits have 4. At each joint, there is one small torsion spring with legs at a 90-degree angle, forcing the claw to remain in a closed grasped position at rest. When the bird or drone is ready to perch, the linear actuator pulls on the cables, which forces the claw to open and increases potential energy in the springs. Once the tension in the cable is released, the potential energy is converted to kinetic energy, causing the claw to quickly grasp onto the perching target and remain grasping until the power source is engaged again.
We try to design our landing gear to mimic that of a bird's landing mechanisms, while also taking inspiration from the previously mentioned Qingdao University of Technology's design. When flying, birds keep their legs tucked under them to increase aerodynamics. When perching, birds will extend their legs down and forward to properly grasp and perch on their desired target. To accomplish these goals, we made use of a driving structure design where the components are all connected to a main body. Qingdao used a small and basic version of this design that was rigid. Our design improved the driving structure by adding the ability for our legs to rotate up and down. Our driving structure was designed to be easily incorporated onto the bottom of a UAV.
On each side is a servo motor that controls the leg's ability to move back and forth, offering up to 120 degrees of rotation. To keep the servos in sync, we designed an axle that runs across the distance of the landing gear. Top designs of the leg fit onto each end of the axle, allowing the legs to also be in sync with the servos. The legs also have an open slot to hold the linear actuators, which controls the open and closing of each claw. When running, the legs will start in a horizontal position. Once the servos are actuated, the legs come down to the vertical orientation, position the claws for grasping. After perching is complete, the servos will be actuated again to restore the legs to a horizontal orientation. The ability to rotate the legs up and down will allow less drag, making flying more efficient when the whole assembly is attached to a UAV.
Taking a look at how most medium-sized avian perch, they're able to open and close their claws upon landing, which brought us to a final design that utilizes a linear actuator to extend and retract our claws. Typically, avians are able to open their claws and extend their legs for a proper landing position. Translating this type of simultaneous movement into our design was not feasible for the overall scope of this project. Approaching this problem with a more mechanical mindset led us to have the claws start closed, then open, and then only close again once an input is received. Several options of actuation were theorized, but a system using linear actuators and bump switches was chosen.
A bump switch located on the palm of the claw triggers linear actuators integrated in the legs to close the claw from the open position. The claws are able to retract again after a threshold is reached in the maneuvering of the UAV/glider that constitutes a change in position. The linear actuator is able to extend and retract with an input through an H-bridge. Having a range of motion of 30 millimeters, the end effector pulls the wires of the claw digits and releases tension once extended. The whole actuation assembly is easily integrated into a 3D printed leg that connects the claw and landing gear.
Along with designing a functioning claw and leg structure that mimics the appearance of and functions of a bird, we're tasked with ensuring the design can grasp onto various targets. In the following video clips, we tested the grasping capability on a 1.6 inch by 1.6 inch square bar, a 2-inch diameter PVC pipe, a 1.5 inch diameter PVC pipe, and a pyramid-shaped bar made up of 3/4 inch by 3/4 inch square bars. The design demonstrated the ability to sense targets via bump sensors and then trigger the grasp onto the. All 4 targets were grasped successfully.
We encountered some challenges throughout the year. For the claw, we initially had a much smaller design, but had to increase the scale when we realized that springs were not commercially available with our specifications. Had we kept our smaller design, we would have needed custom springs, which are expensive and take a long time to get from a manufacturer. The commercial springs we purchased had a very high spring rate, meaning that they were very stiff and required a lot of force to actuate. This is beneficial for ensuring a strong, tight grasp, but can be achieved in the closed position of the claw, but a disadvantage when it comes to actuation power.
With the final decision on passive actuation, we needed an active actuation system that was able to pull the claws open and could quickly release the tension in the springs to ensure the claws had a strong grip. Servos could pull the claws back, but could not release the gearing to close quickly. Instead, we shifted towards an electromagnetic clutch. These would be able to pull the claws open, and when an input was received, the current would be cut and the gearing would release, resulting in a quick release. Upon receiving the electromagnetic clutches, we recognized that they would not be able to supply enough power to displace the cables and open the claw. To combat this issue, we switched to a linear actuator that could supply more power. While the linear actuator will not have the quick release actuation we were hoping for, it is much easier to integrate into the leg landing gear system than the 2 servos would be. As seen in the testing videos, the linear actuators were able to open and close the claw, but there was a noticeable limitation at the end of the actuator's return stroke. The tension required to fully open the claw increases as the springs are loaded and requires manual assistance to achieve full claw extension. With more time, we would have looked into incorporating a linear actuator with a larger gear ratio or one that could provide more force.
The integration of this claw system is a major improvement over current practice because it allows for dynamic grasping and eliminates the need for landing on open flat areas. We hope that this technology will be further researched and prototyped in order to advance the landing variability of the aircrafts. Aside from the mechanical design components, technical formulas, and actuation methods, we gain an appreciation for the living creatures and natural phenomenons that have inspired so many discoveries within the realm of mechanical engineering. Thank you for listening to our video, and we hope you enjoyed learning about our senior design bird claw.